So thanks. Depending on your background, MPI is obviously the right thing to do, and I need to explain to you what Spark is, or Spark is obviously the right thing to do, and I need to explain to you what MPI is. And so what we're going to be doing is something interfacing the two here. And it's worth asking why, and so it's of interest more generally, but as a foot in the door, and I think a particularly compelling use case of certain scientific applications that I'll describe. So we have a new logo, so if you can retweet that or something, we're hoping this goes viral pretty soon. So here's the new logo for Alchemist, which is basically the gateway to get these two things to talk to each other. So I'm going to cover, I have here more than I want to cover, so I'm going to gloss over a few things, so these will be online, but want to emphasize a few things, and I wanted to start off with some thoughts sort of on machine learning more generally that sort of are motivating us, but that I think tap into a pain point that a lot of people may be having. And then talk about Spark. So when we started this a while ago, it was actually hard to answer the question, how well is Spark doing relative to different things, in particular relative to not having it? And so we did a large and detailed study and got an answer to that. And the answer is that you lose a lot of performance. Now that might be not a problem, or that might be a problem depending on your use case, and we'll talk about that. But in a number of cases that is a problem, and so you may want to solve it. And so we're going to solve it with an elephant. We're going to solve it with Alchemist. Alchemist will be the interface between Spark and MPI. We'll see how we do that. There's a bunch of moving parts here, and as a lot of you probably know, in different forms, whether you're on a single machine or a supercomputer distributed data center, communication is the expensive thing. And so it's something that feeds into this, which isn't this, but something Alchemist could call as some communication avoiding work in machine learning as opposed to other sort of communication aware machine learning methods or communication avoiding linear algebra. And there's a number of things that are going to use this that I'll just sort of gloss over at the end. Some of these are sort of standard use cases. Some of these are a little bit different. So the elephant in the room is that, at least in my experience, so I started putting this slide up about 10 years ago, and I'm going to take it down when it's not true anymore, is that in my experience, when people talk about large data, and then it was massive, and then it was extremely large, and then it was big, and it's data science and so on, they oftentimes reveal more about their background and experiences in the data. And so I came at it from sort of a foundational perspective. So somewhere here it says what's sort of the theory of algorithm, the statistical theory. You might be a machine learner and you just say, geez, I need to add some regularization. You might be supercomputing because I just need a bigger machine, or databases and I just need to have something more agnostic and more usable and so on. And so, can we get past this so we're sort of addressing the data sort of for what it is and trying to solve the particular problem. So as an example problem, this is an example problem that I think is not on the lead axis of pain point historically for a lot of internet and social media, but is for scientific problems. And so this predated the work I'll be talking about, but it informed a lot of what we're asking about, and we're feeding these results back into this. So single nucleotide polymorphism. So everyone has the human genome. It's different than sea slugs and monkeys, although 99% of the DNA is the same. But you think there's the human genome. And so in fact, everyone in this room is different, and they're different in a lot of different ways. There's transpositions, insertions, and deletions. The most sort of common way people are different is something called a single nucleotide polymorphism. It's a single site in the genome where a non-negligible fraction of people have one nucleotide or another nucleotide. And there's good genetics reasons why it exists. And so from the perspective of what we're talking about, it's particularly easy to think about as a matrix. So that's a level of abstraction where you have people by SNPs. And so we started this back when HapMap was state of the art. So there's 400 people by a million SNPs. Now you can have tens of thousands of people by millions or more SNPs, and depending on the experiments you do, not in humans, it can be large on both axes. So think of this as a matrix. And I say matrix because if you're doing Spark or databases or whatever, you're not thinking of the data as a matrix. You're thinking of it as a flat table. That's a very different sort of mental object than as a matrix. And so what are you going to do with this? And so what you might do is to say, I want to run PCA. PCA is sort of a hello world analysis techniques. It involves computing a couple eigenvectors, and here's what you get if you project onto the two eigenvectors. And you say, out of Africa, Middle East, East Asia, so on and so forth, what's going on? The Mexicans are stuck in the middle there. So why is that? So this is something you can do in MATLAB and Python and R and so on. Someone wrote the code for you under the hood. You're ignoring that. And so what's going on here? And why are the Mexicans in the middle where they don't belong? Well, it's because we're looking at two principal components, because the board is two-dimensional. If you look at three principal components, what you see is this, and the third one shoots down. And there's good genetics reasons. There's a mixing between Americans, meaning American Indians, and Europeans. So this is a sort of hello world thing that people want to do. And so why do you want to do this? So this is great. You get visual supportive out of Africa hypothesis. It's not altogether satisfactory. And why? One, computing large SVDs. So this was 2,000 by 500,000, which is large by some standards, not large by other standards. It's not a one line in MATLAB or Python or something, or Jupyter or anything, but you can do it. It's not terabyte scale. We'll get to that in a minute. But you don't want to run it. It takes 20 minutes, so that's a coffee break. But you don't want to run it once. You want to run it 10,000 times. You want to run it 1,200 times as part of a cross-validation experiment. Then you realize you made an error. You have to normalize something differently. You rerun the pipeline again. You iterate back. And so it's expensive, but not necessarily just expensive purely in terms of CPU time. And a different thing is that in terms of the domain, geneticists, you tell some geneticists, I got a leading eigenvector, a leading eigensnip. It's a linear combination of a million SNPs. They'll say, who cares? I mean, I can't go to the lab and type that. I can think about actual SNPs. I can think about actual data points. So I might want to get actual columns that capture something. So there's a large body of theory under here. And actually, the results we'll be talking about in a little bit use sort of the column subset selection problem as a way to address a problem like this. And so this is something very related to PCA, but a little bit different in that it gets actual columns. And so a question one might ask is, can I get the actual best K columns from a matrix? And so this is a genetics application. We've seen similar things in astronomy. There, the matrices might be sparse or dense in different ways. But a different type of question you might want to ask. And so what do you want to do now? So one answer is I just want to do this small enough on my single machine. Another example is, well, I want to get larger. And where do you go if you get larger? And so let's talk about Spark. So I was in AmpLab, and that's how Spark was developed. And so it was a lot of interest in that. And so how might it perform? So where are you going to run your calculations? In the 99% use cases on a single machine, I mean, you heard this nice talk about IPython and Jupyter. And so, I mean, at Berkeley, there's a data science division, and the freshmen are starting with that. And and probably a lot of you know, a consultant whose deliverable at the end of a 3-month project is a notebook. And so, single machine, a lot of people get introduced here. And, can you make that transparent? You're going to go to a supercomputer or distributed data center. So the 1% either live here or here, depending on the use case and the application area. And so we're going to consider those two. So Spark, as probably many of you know, is a cluster computing system, and it's interoperable with Apache Hadoop. The leading order bit is that Hadoop wouldn't maintain some state, and so it was expensive for iterative algorithms. Spark could keep state, and so it was good for iterative algorithms, which is the bread and butter of a lot of machine learning. Nice, easy to use API. MPI is message passing interface. It's a specification for developers. It's a little bit lower level, and there's a bunch of implementations, Open MPI, and so on. So the Spark architecture, what you need to know is it's a data parallel programming model, resilient distributed data sets, think distributed array type. RDDs can be cached in memory between iterations. That allows you to do the iterative algorithms. And the driver forms a DAG and schedules on executors. And the sort of basic unit of operation is an RDD. One RDD produces another. And so the overall DAG is broken into stages, and communication happens only between stages. If the computation you're running conforms with that, it's great. You do something, you communicate, you iterate. And for a lot of things, you want to do joins, you want to do selects, that's perfectly fine. And for some linear algebra algorithms, you want to iterate over them. I mentioned linear algebra because that's the bread and butter of a lot of machine learning. The canonical example you should have in mind is not PageRank. That's not a basic thing. It's just a few steps of a power method. A more basic thing here is a QR decomposition. And so for a QR decomposition, if you're familiar with it, and if you're not, basically you want to get the 1-1 element of a matrix. You have to compute something. And then to get the next column, you have to take the next column, you have to remove the piece along the first column and then normalize it. So the 1, 1, and 1, 2. And then you get the third column, and you have to remove the piece along the first 2 and then normalize it. So it's a 1, 1, 1, 2, 1, 3. And so you get this triangular thing. And so it's a much sort of more complicated communication pattern. And so you might expect that if you're going to force it to go through something like this, you're going to lose a lot. And we'll see that that's the case. So why do linear algebra? Widely used, easy for non-experts, entire ecosystem, and so on. Cons. If you really are doing simulations and that last factor of 2 matters, don't be doing this, right? So you want to do this if you're fitting within an ecosystem, you're doing data analysis, you're doing the cross-validation, you're doing it 1,000 times, you go out for coffee for that 20-minute coffee break, you come back, and you realize you made a mistake, you iterate this. So there's a larger ecosystem, but if that last factor of 2 matters, we're not going to improve that, but we'll improve what you lose up here. So we wanted to provide implementations of low-rank factorizations. NMF CX is the column subset selection problem to get actual SNPs rather than eigensnips. It uses randomization under the hood. There's a lot of nice theory there, so it's sitting on good theoretical foundations. It's not just some ad hoc method. And I mention that because, in a sense, there's a lot of work on running a deep neural network with convolutional layers, a few skip layers, lots of parameters, and you're running an SGD, and there's acceleration knobs and adaptivity hyperparameters, and lots of data sets out there. And in a sense, anyone can run that, right? I mean, you just run that and you get something, and if you fail, you don't publish it, you don't push it into production. If you succeed, you publish it. So there's that bias. A very different question is to say, I just want to run PCA. I want to get a best rank 20 eigenvector on 50 terabytes of data. Can you do that? So that's what we're constraining ourselves in that sense. So sort of very basic problems. We want to apply low-rank factorization methods, terabytes, scale data. Understand these trade-offs. Spark on commodity machines, on HPC platforms, which is a much harder stress test. Quantify scalability gaps, and if there's gaps, improve it. So there's a bunch of science drivers that I sort of hinted at before. Data sets, the conversion here is not bad, not good, but it's 1 to 18 terabytes in mass spec imaging, in nuclear physics, and ocean and atmosphere. So there's very particular use cases here. And the second thing about the neural network or a lot of machine learning pipelines is oftentimes you don't need the right answer, right? I mean, you need an answer. It doesn't need to be right. It needs to be not completely wrong, so it needs to be correlated with being right. But it doesn't need to be very high quality, very high precision, because you're going to feed it into a pipeline, or you're going to feed it operationally, you're going to feed it into an ensemble method statistically. If you want best rank 20 approximation with some guarantees, that's sort of a well-defined problem, and so you may not need that, but if you do need it, that's a harder test to stress test against. And these are applications where they want that, and so we were looking at that. So we have an empirical evaluation of the performance, and I'd want to give you a summary of that empirical evaluation. This is about 2 years old by now. Roughly, it's the following. NMF is not a problem. So I say NMF here. You should raise your hand and say, what problem are you solving? NMF is not a problem. It's 1,000 problems. Right? There's 1,000 different types of it, and depending on the type, you'd get the same or very different numbers. So this particular type is a particularly nice one. It makes a niceness assumption so that you can solve it roughly with a tall, skinny QR, one pass over the data. And so if you can do one pass over the data, you might think the communication's not that bad. And what you see is when you run NMF, you lose a factor of 2 to 4. So you're in Spark, you run these computations, compared to just MPI without this. So if you want the convenience of sitting in Spark, that's what you lose. So with the factor of 2, you're in trouble. Factor of 4, fine. So don't be doing this if you're running large-scale computations, and that matters. But if you're fitting within the analytics ecosystem, that may be perfectly fine. So you need to go for a slightly longer coffee break. PCA is like QR. It has a more complicated communication pattern. And what you see is at the same size scale, you lose a factor of 10 to 20. So that starts to get to be a little bit larger. That might be something you don't want to do, but fine, I'll live with that. That's on 2 terabytes. What about when you go to 16 terabytes? Now you lose a factor of, 13 to 26. If you get larger, you get worse still. So what you see is that the sort of core principle of CS is violated. You anti-scale. You don't scale. And you anti-scale because you don't have any control over the communication. And so that's a serious problem. So blue is computation on some number of nodes. Blue, Spark, you're a factor of 2 or 3 worse than MPI, but in all of those it goes down. Communication is purple and orange, and it gets worse. So as the number of nodes increases, it just gets worse. There it's a factor of, 3. On the 2 terabyte data, you go to 16 terabytes, and it's an order of magnitude. So there's a massive performance hit in that sense. If you're doing NMF, the more communication-friendly thing, everything will go down. So the leading order bit that I'll just gloss over in this time is MPI versus Spark. With favorable, we're looking at tall, skinny data. We're not fat in both dimensions. So if you're fat in both dimensions, you're going to have to block up the matrices. You're going to have additional communication. So this is then the nice use case. Data's well posed and so on. You're going to lose 4 to 24, 4 to 40, depending on whether you include I/O. Spark overheads are orders of magnitude in the computation. That's just the communication footprint. And it anti-scales. So this, I was at a meeting a couple of years ago, and one of the leads at Databricks, was there for 3 days and asked questions during one talk during 3 days, and it was 3 questions on this talk when Alex Gittins gave this talk. So it's easy to beat up on people, right? It's hard to beat up on them fairly, and so I think this is, as of 2 years ago, the state of the art in terms of the evaluations and really sort of stress test it, and they went back, and their engineers are trying to deal with these sort of performance gap issues. From our perspective, we're going to say, can we efficiently interface MPI-based code with Spark? So the short answer is yes. And so Kai Rothage is here. He'll be around and he'll give a presentation. He'll have a poster on more details on this morning on Alchemist, or tomorrow morning. And Alchemist is going to be an interface. So since we're going to lose 4x or more and we anti-scale, an HPC person is going to say, why don't you, if you're losing 4, you're losing 40 for the non-trivial linear algebra problem. Why don't you just run MPI? Fault tolerance in Spark can't be that good, right? MPI is not going to fail 39 times in a row, right? And if it fails 39 times in a row, you're probably going to succeed on the 40th time. So just do that and you still win, which is a fair observation if you don't think of the whole ecosystem. And so, the idea is the following. So Spark is doing this thing. And the idea is you want to hide stuff from people. It's not very low level like C and Fortran and C++. You want sort of an interface that hides some things. So let's hide some stuff. Let's, within the Spark, do something. What we're going to do is have a gateway write down to MPI and do stuff and write it back and see if, what we lose and if we can solve this problem. So alternative approaches is write to HDF slow file I/O, there's data layout reissues. There's some other bridges. They assume sparse data sets, which is, not the 99% use case, maybe the 80%. But so it's bread and butter machine learning, but there's oftentimes you get dense matrices. Apache, Ignite, and Luxio requires C++ interfaces, manual data layout. So what we want to use is Alchemist. Alchemist uses in-memory transfer. It's going to provide data relayout transparently, and it's going to handle dense data sets in addition to sparse ones. So we have Spark. This is what the user sees. There's a gateway here. It's going to call MPI. Spark's going to send the metadata for I/O to Alchemist. That's going to use sockets. We'll see the picture for that. It'll send commands to the Alchemist driver, and Alchemist will repartition the matrix for MPI. Right now it uses Elemental. It could use other things, but we're using Elemental right now. And it's going to coordinate workers and executing MPI codes, and it's going to send the output back to Spark. So the Spark driver talks to the Alchemist driver via sockets, the executives via sockets. MPI, I don't know what's going on down here, right? I want to be ignorant about that. Maybe I do know, but if I do know, I'm not going to tell you because you don't want to know, right? So we want to be hidden from that. So that's the whole point of this. So we're going to want to exploit locality to reduce communication. All right. And sort of there's a lot of moving parts here. Something sort of to have in your mind is I want to do matrix multiplication. And so if you're in RAM, it's easy to take a transpose. You just take a transpose. If you're not in RAM, you don't have random access. You can't just take a transpose. So how do you do that? So what we want to do is minimize communication between Spark workers and Alchemist workers. Spark stores these things. There's no matrix. There's no rows. There's no columns. This is an RDD. Everything else we're putting on top of that, right? So it stores it in row distributed format. So by row, I mean matrix row, not database row, although there's some relationships, while also switching between Spark distributed schemes imposed by, matrix distributed schemes imposed by Spark and numerical linear algebra codes. And so we currently have a bunch of operations implemented: send, retrieve, transpose, matrix multiply, and then a bunch of more matrix, bread and butter, k-means, low-rank approximation, sort of machine learning, we'll call them primitives, linear algebraic primitives for machine learning. libskylark is a randomized linear algebra code from IBM. We'll interface with that also. So here's your matrix. And what we want to do is, this is going to require an expensive shuffle in Spark. So matrices are row partitioned, and one has to be converted to column if you're multiplying A times B. If you remember, you can write A times B as columns of A times rows of B, or rows of A times columns of B, depending on how you want to write it. But it's one of one and one of the other. So this is going to require an all-to-all shuffle that fails even for matrices that could fit in memory. So we're not even at terabyte scale, right? At much more modest scale, we're going to have this is going to fail even for matrices that could fit on one executor. These absolute numbers don't mean anything to you yet, but just to give you absolute numbers, I have A and B, and it's 8 gigabytes and 5 gigabytes. The product's 50 gigabytes. I have 2 nodes for Spark and Alchemist. Spark fails after 400 seconds. When I say Spark, I mean the user's seeing Spark and they call it, and that's all there is. When I say Alchemist, the user sees Spark, but under the hood, we're calling this gateway, doing stuff we don't want to know about, right? So when I say Alchemist, the user sees Spark, but it calls MPI via this gateway. Send is 35 seconds, receive is 56, and compute is 200. So is that good or bad in terms of absolute? Well, it's better than failing after 400 seconds, but is that good or bad? There's a bunch of reasons why things fail. There's timeouts. This is a sort of a small thing, but for the larger things, there's a range of timeouts. There's a range of reasons why things fail. There could be a straggler. There's a bunch of different. Right? This particular one, I don't remember why they failed, but at the larger scale, there's a bunch of reasons why they fail in terms of straggling and timeouts and things like that that just Spark engineered into the system. I'm going the wrong way. Now, same setup except 24 and 4.8 gigabytes. The product is 150. Now you're failing after 30 minutes, so 30 minutes is a natural timeout increment of length. Send is 80 seconds, receive is 36, which is, the same as the previous ones to a factor of 2 or 3 or whatever. And compute's 98. This number is smaller because now we have 10 nodes rather than 2. But the point is, so this is taking 2 or 3 minutes and it's not failing after 30, so that's good. I'm just going the wrong way again. So now let's go to truncated SVD, which is a more complicated problem. Think of this like QR. So this is Alchemist. I'm going to look, and then I'm going to show how Alchemist compares to Spark in a second. But Alchemist, blue is read or write. Blue is Spark to MPI. Orange is MPI to Spark. Green is compute. So there's a bit on each side. That's how they scale, and compute dominates. So you're not paying your order. Remember the plot a few slides ago is this brown and blue is order of magnitudes larger. So that's not what it is here. That's Alchemist. Now let's look and.
Actually increasing, that's a remarkably good chart given where you are, right?
So I try to brag about how wonderful we are, but it's always great when you, in the interest of time, are rushing over something and someone in the room interrupts and says, that's actually remarkably good.
Yeah.
So I'm not going to argue with that. If I had more time, I'd elaborate on that point further. But so this is actually by the standards of HPC, not by the standards of distributed data systems. Extremely good. I mean, the Cray people almost fell off their chair when they first saw this. I mean, they said, wow, that's remarkable. So this is actually very good. All right. There we go. If I had a chair, I'd fall off, but I'm afraid to try and fall off the podium here, so I won't. So this is actually remarkably good. So the sum here is, 315, 61, so that's 400. So now let's look at how this compares to not using it. And so what you see here is that's what you saw before. It's all green now. And so this is Spark calling Alchemist, calling MPI under the hood. Blue is Spark without that. So on the smallest thing, it runs. It doesn't die. For the rest, it dies after 30 minutes. So one, that's remarkably good, and it's better than extremely bad. So we have 2 pluses going for us. This is 2.2 terabytes. This is 4. This is 8. This is 16 or 17.6. And just in the interest of time, I'll not go into the details except to say blue is load, green is SVD, receive is yellow, and overall. So the point of comparison is basically green to orange. So what you're losing in terms of communication is not the order of magnitude. You're losing from to, a little bit there, and that's what it is. But that's a factor of 2 or 3. It's not a factor of an order of magnitude. We can run this on PCA, terabyte scale. I wish I had a paper to point you to here. We solved the climate problem. It's not the sort of problem that gets published because we found an interesting signal in the climate data set on terabyte scale. That interesting signal was that at high frequency, so they had a lat long, but they wanted a 3D climate field now and time resolved, and at very high frequencies, there's some systematic problem with their measurements. And we diagnosed that. So that's not the sort of thing climate scientists want to see in a publication, although you got to get the data right. But from our perspective, we found something interesting that was in the data that they weren't able to find at that scale. This is a visualization of one of the eigenvectors. So Alchemist has a bunch of next steps. Communication avoiding machine learning, let me just say, there's a bunch of things in communication avoiding linear algebra that take a core problem and basically say, shuffle around the for loops in different ways to minimize communication, not computation. And you typically want to get the same computation footprint, but have communication be less. And that's very different than what happens in machine learning when you say, I just want to solve a more sophisticated iterative algorithm, and I want to minimize number of iterations, and I'm not going to ask how long each iteration takes, which is a common thing in machine learning. And this is a student who defended his thesis maybe a week or 2 ago, really sort of bridged those together very nicely. Said we're going to use core results from iterative linear algebra, Krylov subspace methods, to solve machine learning problems, L1 regression, these sorts of things. So going beyond core linear algebra to really solving non-trivial machine learning problems. And you gain factors of, let me show you the page of numbers. Depending on S is the unrolling factor, block size, you gain factors of, 2 to 3 for one set of parameters, and 3 to 6 for some other set of parameters. That doesn't matter if you're paying orders of magnitude in communication. That does matter if you've pulled that down to a factor of 3. And so this is not Alchemist. It's something Alchemist could call instead of Elemental if it wanted. So we don't have that in place yet, but you could tie the two together. And we applied it to a bunch of other problems. And I'll just have a teaser if you want to go look on my web page or something. Once you've done Alchemist MPI interface, can you do other things? So sorry, once you've done Spark MPI interface, can you have X MPI, where X is something else? Say an IPython notebook, a Jupyter notebook. There's Ray, there's some large-scale graph processing, there's second-order optimization methods, which would also fit sort of cleanly into this. So this is a little bit less mature. We don't have these things integrated with the Alchemist structure yet, but I don't know, have me back in a year or two, and I'll tell you about those results then.
Thank you very much. This is a great talk. Anybody have any questions before I fling my softballs?
Thank you. So you mentioned you considered Apache Ignite as well, or Hazelcast. So the statement that you would have to do C++, why?
There was a bunch of things. We wanted a very clean interface. We wanted to work within Spark. There was a couple of constraints. We didn't want to do extra low-level coding. We didn't want to lose a factor. So we're going to have a in-memory in Spark, and we're going to transform it. So there's going to be a 2x copy of memory. We didn't want a third. So there was a bunch of other things that we eliminated basically because we wanted the interface to be clean. We didn't want the factor of the extra factor of 2, a third copy of memory. And so that's why we settled on this. A couple of these things have evolved relative to 2 years ago in making some of the design decisions. So if they've improved something since then, may not know, but at least 2 years ago when we were first designing this, those are the considerations and the things that the ways we were looking at interfacing Spark to MPI. We ruled out those for those reasons.
Anyone else? My quick softball question. The slide you flashed over had the word ScalarPack on it. Are you using ScalarPack in the implementation, or have you done your own MPI framework around LAPack and the local stuff?
No, we don't want to touch anything. So the communication avoiding stuff, some of the stuff forward looking that I said we could call later, we may call. We're using Elemental right now.
Okay.
And depending on user demand, et cetera, we could call other things and interface in other ways, but we don't have all those worked out yet.
The observation is Jack Dongera's ScalarPack team, they've got just a vast cornucopia of these highly distributed algorithms that built their own MPI, and some of the very sophisticated stuff that they've done is quite impressive to look at.
Yeah, so I was on the phone with him, I don't know, 2 weeks ago for something. A lot of these techniques, something I glossed over, methodologically use randomization and random projections, and it's not clear you can do well, but question, can randomized linear algebra beat LAPack in wall clock time? And the short answer is yes. And so there's interest from his team and other ones to try and interface randomized techniques for dense and sparse linear algebra into his machinery. And then it raises a whole host of issues in terms of, do you want machine precision? Do you want not? I mean, you can do it at machine precision level if you use it as a preconditioner. You can use it not at machine precision level if you do iterative algorithms on a roll like the way we were talking about it. So this is on his radar, and I've been talking about that. And I think that there's a very non-technical question here, which is how best, it took us, I can't tell you how much effort just to answer the question, can we get a fair comparison of linear algebra in Spark versus MPI? And it was not a technical question in the sense that some people said obviously yes and obviously no. It just takes a lot of sort of education in different areas to get to the point where you can ask a fair comparison. So it's the same thing there, right? What's the use case? Is it a DOE, a supercomputer use case? Is it a distributed data system? And so we're trying to carve that out to bridge these techniques there also, yeah.
Very good. So thank you very much again. That was